Module 16, Lecture B, Tree Regularization. By the end of this lecture, you will be able to explain cart construction and impurity reduction in practical terms, diagnose overfitting and instability in decision trees, and apply pruning and structural constraints to improve generalization. Tree mechanics: cart, split, building. Cart, or Classification and Regression Trees, builds a decision tree by repeatedly asking yes or no questions about the data. It starts with all training examples in one root node, then chooses a feature and cutoff that best split the data into two groups. For classification or regression, each split is selected to organize the examples more clearly around the outcome being predicted. Cart chooses a split by testing questions that divide the data as cleanly as possible. For numerical features, it tries different thresholds, and for categorical features, it tests ways to group categories into two sides. The best split creates child nodes that are more internally consistent than the original node, making later decisions simpler. CART builds decision trees greedily, choosing the best split at each node rather than planning the whole tree in advance. This makes the method efficient and easy to interpret, but early splits can strongly shape the final tree. The same splitting process repeats within each child node, creating different paths through the data. Because this can fit the training data too closely, overfitting must be managed carefully. Impurity reduction. Decision trees choose splits by reducing impurity, meaning they try to make each resulting group more uniform. At each node, the algorithm looks for a split that separates mixed outcomes into clearer groups, such as applicants with different default risks. A good split reduces uncertainty and helps the tree make more accurate predictions. CART builds a decision tree by testing possible splits and choosing the one that most improves purity at each node. Numeric features are split using thresholds, while categorical features are grouped to make the resulting child nodes more uniform. These choices are driven by impurity reduction in the training data, not human intuition, so the tree focuses on the best immediate split, rather than a perfect overall solution. Impurity reduction shows both the value and danger of decision trees. Good splits can reveal meaningful patterns, but too many splits may fit random noise in the training data. A tree can look very accurate on past data while performing poorly on new cases. So the goal is to create informative nodes without losing the ability to generalize. Python code impurity reduction. This example explains impurity reduction in CART by comparing possible splits on a single feature. The best split is the one that produces the greatest increase in purity. We import NumPy to handle numerical calculations efficiently, especially with arrays. We also use Scikit-Learn for machine learning tools, including its decision tree classifier, which builds classification models by splitting data based on feature values to make predictions. We define two arrays to study loan behavior. One records how many payments each loan missed, and the other shows whether each loan defaulted. Together, they help analyze the link between missed payments and defaults, which can guide split choices in a decision tree model. The Gini function measures how mixed a set of labels is. If there are no labels, it returns 0 impurity. Otherwise, it finds the proportions of the two classes, 0 and 1, and computes impurity as 1 minus the sum of their squared proportions. The result is lower when one class dominates, and higher when the labels are more evenly mixed. The code identifies possible split points for a decision tree by choosing thresholds between sorted feature values. It then computes the Gini impurity of the full set of default outcomes as a baseline. Each candidate split can be compared against this baseline to see how much it improves group purity. To find the best split in the data, we first set up values to track the strongest impurity reduction found so far. The best gain starts below any valid result, and the best threshold is left empty until a better split is identified. This lets us compare each candidate split and keep the threshold that gives the greatest improvement. For each possible threshold, the data is split into two groups based on whether missed payments are at or below that threshold or above it. The algorithm measures each group's size, computes the weighted Gini impurity after the split, and compares it with the original impurity to find the reduction. The threshold with the largest impurity reduction is kept as the best split. The missed payments data is reshaped into a single feature column so it can be used by a Scikit-Learn model. A decision tree stump, meaning a tree with only one split, is then created with a fixed random state for reproducibility. Fitting the stump to the default labels trains it to choose the best threshold based on impurity reduction, which can then be compared with the manual calculation. The process compares a manually calculated best split point with the threshold selected by a decision tree classifier. It retrieves the tree's chosen threshold, prints the Scikit-Learn version for reproducibility, and displays both threshold values. Formatting the classifier's threshold to one decimal place makes it easy to confirm that the manual calculation and the model agree. This script shows how a decision tree chooses a split by reducing Gini impurity. It tests possible thresholds for missed loan payments, calculates the impurity reduction for each one, and identifies the threshold that gives the greatest purity gain. It then fits a simple Scikit-Learn decision tree to confirm that the model selects the same split. The result illustrates the basic idea that decision trees choose splits that make the resulting groups as pure as possible. Tree complexity. Tree complexity describes how detailed a decision tree becomes as it adds more splits. A deeper cart tree can use more variables and capture subtle patterns or interactions that simpler models may miss. However, too much complexity can cause overfitting, where the tree learns random noise instead of patterns that work well on new data. Tree complexity depends on factors such as depth, number of leaves, and how much data supports each split and final leaf. More complex trees can find very specific patterns, but those patterns may be unreliable when based on only a few observations. This matters in areas like medicine, where a tree might identify a rare patient group but have limited evidence for its prediction. In short, complexity affects not only the model's structure, but also how much confidence we should place in its results. Tree complexity in CART is driven by how much each split reduces impurity. Early splits usually capture the strongest patterns, while later splits may add only small improvements and can start fitting noise or rare cases. A good tree balances detail with simplicity, capturing meaningful structure while still generalizing well to new data. Overfitting control. Tree instability. Tree instability means a decision tree can change a lot when the training data changes only slightly. Because each split is chosen locally to reduce impurity, a small change can alter an early split, which then changes the data used for later splits. As a result, two trees may emphasize different features, such as income or age, even when the underlying problem is the same. Tree instability is closely tied to overfitting because deep, flexible trees can learn random noise instead of only real patterns. As decisions are based on smaller groups of cases, the tree may treat rare or outdated patterns as meaningful. This can make the model look accurate on training data, but produce unreliable predictions on new data. To diagnose tree instability, test whether a decision tree gives similar splits and important variables when trained on slightly different data samples. If small data changes lead to very different explanations or large prediction shifts, especially near decision boundaries, the tree may not reliably reflect the underlying process. In that case, limiting tree depth or using ensemble methods can help make the model more stable. Python code, tree instability. Decision trees can be unstable because small changes in the data may change the early splits and lead to a different tree. Regularization helps reduce this sensitivity and makes the model more stable. We import the main tools needed for a simple machine learning workflow: NumPy for numerical arrays, Matplotlib for visualizations, and Scikit-Learn for modeling. From Scikit-Learn, we use a data generation tool to create synthetic classification data and a decision tree classifier to build and train a decision tree model. We create a small synthetic classification dataset with 240 samples and 4 features using Scikit-Learn. 2 features are informative for predicting the target, while the others add no redundant information. A fixed random state makes the dataset reproducible, allowing us to study how decision trees respond to features with similar importance. Before training any models, the code verifies that the dataset has 240 rows and 4 columns. If the data does not match this expected structure, it raises an error. This early check helps prevent model training problems by confirming the data is in the required format. A random number generator is initialized with a fixed seed of 42, so the bootstrap samples can be reproduced. 2 empty lists are then prepared to record which feature is chosen for the first split in deep decision trees and in regularized decision trees. This will allow comparison of how often each feature is selected first across different samples. We create 12 bootstrap samples by repeatedly drawing random row positions from the target data with replacement. Each draw selects matching rows from the feature data and target values to form a new sample. This simulates multiple versions of the original dataset and helps evaluate how stable the decision trees are. A decision tree classifier is created with a fixed random state, so the results can be reproduced. The tree is allowed to grow without depth or leaf limits, then trained on a bootstrap sample of the data. After training, the feature used for the first split is recorded to see how often different features become the initial decision point across samples. A regularized decision tree is trained on each bootstrap sample by limiting its depth and requiring a minimum number of samples in each leaf. These limits reduce overfitting by keeping the tree simpler. After training, we record the feature used for the first split to study whether regularization makes the tree's initial decision more stable. We label the 4 features so each index is easy to identify, then count how often each feature is used as the first split in the deep trees. We do the same for the regularized trees, making sure all 4 features are included, even if some are never selected. These counts let us compare which features each tree setup tends to choose first. The code first prints the Scikit-Learn version to support compatibility and reproducibility. It then shows how often each feature was selected as the first split in both deep and regularized decision trees, pairing feature names with their counts for a clear comparison between the 2 configurations. To compare the first split choices for the 2 tree settings, the plot first assigns x-axis positions based on the feature names and sets a consistent bar width for spacing. It then creates a Matplotlib figure and axis with a chosen size, preparing the chart layout for the grouped bars. The code builds a bar chart comparing which features are chosen as the first split by 2 decision tree settings. It places the deep tree counts slightly to one side of each feature and the regularized tree counts slightly to the other. making the two sets easy to compare. This shows how often each feature becomes the first split across different samples for both tree configurations. The plot summarizes which features were chosen as the first split across bootstrap samples. It labels the axes to show the root feature and how often it was selected, uses feature names for readability, and includes a legend to compare deep and regularized trees. The visualization is then displayed for analysis. This script shows that decision trees can be unstable because small changes in the training data may change the first split. It creates bootstrap samples from a dataset and compares unrestricted deep trees with regularized trees that limit depth and require larger leaves. By counting which feature is chosen first, it shows that deep trees usually vary more, while regularized trees are more consistent. The printed results in bar chart illustrate how regularization improves decision tree stability. Minimum sample limits. Minimum sample limits help decision trees avoid overfitting by preventing splits based on too few observations. As data groups get smaller, the tree may start learning noise or rare cases instead of patterns that generalize. Requiring enough samples before a split makes decisions more reliable and based on broader evidence. Minimum sample limits help prevent decision trees from overfitting by stopping them from creating branches based on very small, unreliable groups of data. When these limits are too low, the tree may fit the training data closely but fail on new cases. Raising the minimum samples needed for a split encourages the model to learn stronger patterns, making its results more stable and easier to interpret. Choosing minimum sample limits in decision trees is a balance between reliability and flexibility. The right limit depends on the dataset size, how rare the outcome is, and the model's purpose. Limits that are too loose can make results unstable, while limits that are too strict can hide useful patterns. Comparing training and validation performance helps set leaf sizes that support credible decisions in applications such as credit risk or equipment failure prediction. Python code. Minimum sample limits. When training trees on noisy data, compare different minimum leaf sizes. Very small leaves can memorize random patterns in the training set, while larger leaves often give more stable validation results. We begin by importing the main tools needed for the workflow: NumPy for numerical work, Matplotlib for visualization, and Scikit-Learn for machine learning. From Scikit-Learn, we use tools to create a synthetic classification dataset, split it into training and validation sets, and build a decision tree classifier. Together, these imports prepare the environment for data handling, plotting, and classification modeling. We create a small, noisy classification dataset with Scikit-Learn's Make Classification function. It has 800 samples and 2 informative features, with no redundant features. To make the data more realistic, 18% of the labels are flipped, the classes are moderately separated, and a fixed random state ensures the results can be reproduced. The dataset is split into training and validation sets using Scikit-Learn's train-test-split function. 35% of the data is reserved for validation, while stratified splitting keeps the class proportions the same in both sets. A fixed random state makes the split reproducible each time the code runs. Before training, the code verifies that the number of training samples matches the number of labels. This check ensures every feature set has a corresponding label. If the counts differ, it raises an error because the model cannot learn correctly from mismatched data. We test several minimum leaf sizes for a decision tree to see how they affect performance. As the model is trained with each setting, we record the training score, validation score, and number of leaves. These results help show how leaf size influences accuracy and overfitting. The loop tests several minimum leaf sizes for a decision tree classifier. For each setting, it trains the model, records its accuracy on both the training and validation data, and stores the resulting number of leaves. This shows how changing the minimum leaf size affects both model performance and tree complexity. The code prints the Scikit-Learn version for reproducibility, then displays a compact summary of decision tree results. For each minimum leaf size, it reports the training accuracy, validation accuracy, and number of leaves, with scores rounded for readability. This makes it easy to compare how leaf size affects performance and possible overfitting. Create a plot that compares training and validation accuracy across different minimum leaf sizes. Each accuracy curve is shown with circular markers and a clear label, making it easy to see how leaf size affects model performance. The plot title highlights the main idea. Minimum leaf size helps control overfitting in a decision tree. The plot is labeled to show that the x-axis represents the minimum number of samples required in each decision tree leaf, while the y-axis shows model accuracy. A logarithmic x-axis makes it easier to compare leaf sizes across a wide range, and the y-axis is limited to the relevant accuracy range. A legend is added so the training and validation accuracy lines can be clearly distinguished. The code finishes by using the Matplotlib show function to display the plot. This lets us compare how training and validation accuracy change as the decision tree's minimum leaf size varies. This script shows how the minimum leaf size in a decision tree affects learning on a noisy classification dataset. It trains trees with leaf sizes from 1 to 80 and compares training accuracy, validation accuracy, and the number of leaves. Larger leaf sizes usually lower training accuracy, but can improve or stabilize validation accuracy because they reduce overfitting and create smoother decision boundaries. Feature constraints. Feature constraints reduce overfitting in decision trees by limiting which predictors the tree can use or how many it considers at each split. This helps prevent the model from building overly complex branches around patterns that appear only in the training data, such as a temporary outage. As a result, the tree is more likely to capture the real structure of the problem and perform better on new data. Feature constraints make decision trees more stable by preventing small differences in the training data from overly shaping the tree. Without them, a tiny gain in impurity reduction can cause one feature to dominate, making the model's reasoning change across runs. Constraints reduce this sensitivity, encourage more meaningful predictors, and improve interpretability in settings where consistent decisions matter. Feature constraints should balance model performance with domain knowledge. Remove predictors that are unlikely to generalize, such as identifiers or irrelevant timestamps, and limit features at each split to reduce dependence on any single strong signal. At the same time, avoid over-restricting the model, since tasks like fraud detection may need several signals. Thoughtful constraints improve generalization, interpretability, and reliability on new data. Python code feature constraints. This example compares unrestricted and constrained feature choices in decision trees. It shows that limiting feature choices can reduce overfitting and make the model more stable. We import NumPy for numerical work and use Scikit-Learn for machine learning tools. From Scikit-Learn, we use a dataset generator for synthetic classification data, a utility to split data into training and testing sets, and a decision tree classifier. Together, These imports prepare us to build and evaluate decision tree models with different feature constraints. We generate a repeatable synthetic classification dataset using Scikit-Learn. It contains 800 samples with 20 features, including 4 informative features and 4 redundant ones, split into 2 classes. To make the task more realistic, 8% of the labels are flipped, and the class separation is set to 0.8, so the classes remain moderately distinct. This code validates that the generated data has the expected shape before analysis continues. It checks that the feature data has 800 rows and 20 columns, and that the target data has 800 values. If the dimensions are wrong, it raises an error to signal that the data structure is not correct. The dataset is split into training and testing sets using Scikit-Learn's train-test-split function, with 35% reserved for testing. Stratification keeps the class proportions balanced in both sets, and a fixed random state makes the split reproducible across runs. We train an unrestricted decision tree classifier with a fixed random state, so the results are reproducible. Because the tree has no limits, it can learn complex patterns from the training data, but it may also rely on noisy or less useful features, increasing the risk of overfitting. We build a decision tree classifier that considers only 4 features at each split. This helps reduce overfitting by limiting how much the model can depend on any one feature. A fixed random state makes the results reproducible, and the classifier is then trained on the input features and labels. We compare the unrestricted and feature-limited decision trees by measuring each model's accuracy on both the training data and the test data. Training accuracy shows how well a model fits the data it learned from, while test accuracy shows how well it generalizes to new data. If a model scores high on training data but much lower on test data, it may be overfitting. Compare the first feature chosen at the root of 2 decision trees, one trained without feature limits and one trained with a limit on features considered at each split. This shows how early feature selection choices can change the structure of the resulting trees. The output first reports the Scikit-Learn version to support reproducibility. It then compares training and testing accuracy for an unrestricted decision tree and a feature-limited tree, helping show performance differences and possible overfitting. Finally, it reports each tree's depth, number of leaves, and root feature index to compare model complexity and how feature choices affect the tree structure. This script shows how limiting the number of features considered at each split affects decision trees in Scikit-Learn. It trains one unrestricted tree and one tree limited to 4 features per split on a synthetic dataset, then compares their training and testing accuracy. The unrestricted tree tends to overfit, while the feature-limited tree gives more balanced results and may generalize better. The script also compares tree depth, leaf count, and the root feature to show how feature constraints can change the tree's structure and decisions. Pruning guidance. Cost complexity pruning. Cost complexity pruning simplifies a decision tree by removing branches whose small accuracy gains do not justify added complexity. This helps prevent the tree from fitting noise or unusual patterns in the training data. The result is a simpler tree that focuses on more stable relationships and generalizes better to new data. Pruning a decision tree means simplifying it to balance training accuracy with a smaller, more reliable structure. A very large tree may fit the training data well, but it can be harder to interpret and may perform poorly on new data. By removing overly specific or insignificant branches, pruning can reduce training accuracy slightly, while often improving generalization, such as in medical or credit risk models. Cost complexity pruning simplifies decision trees by balancing predictive performance against tree complexity. It helps avoid trees that are too shallow or too deep, improving performance on new data while keeping the model easier to understand. The result is a more stable tree, which is important in areas like insurance pricing and fraud detection, where accuracy and robustness matter. Python code, cost complexity pruning. This example illustrates cost complexity pruning, which reduces tree detail to improve generalization. The pruning plot helps identify a useful alpha value for balancing simplicity and performance. We begin by importing the main tools needed to build and evaluate a decision tree classifier. NumPy supports numerical work, Matplotlib helps with plotting, and Scikit-Learn provides the machine learning utilities. From Scikit-Learn, we load the breast cancer dataset, split it into training and testing data, and use a decision tree classifier to model the classification task with cost complexity pruning. We load Scikit-Learn's breast cancer dataset, a built-in dataset for classification. The input features are separated from the target labels, which represent the outcomes the model should predict. This separation prepares the data for training and evaluating a machine learning model. The code verifies that the featured data and labels have the same number of rows, so every data point has a matching label. If they do not match, it raises an error to stop training with misaligned data. This helps prevent incorrect model behavior. The dataset is split into training and testing sets, so pruning can be evaluated on unseen data and its generalization can be measured. Using Scikit-Learn's train-test split, 30% of the data is reserved for testing. Stratified splitting keeps the class proportions balanced, and a fixed random state makes the results reproducible. We first build a detailed decision tree with Scikit-Learn's decision tree classifier, using a fixed random state so the results are reproducible. This baseline tree helps identify where pruning may be useful. We then compute the cost complexity pruning path on the training data to get alpha values for different pruning strengths, leaving out the final value because it would produce a fully pruned and usually unhelpful tree. To make pruning analysis easier, we select a small representative set of alpha values instead of using them all. We generate 12 evenly spaced positions across the available range, then use those positions to choose matching alpha values. This smaller set is easier to review and can be used to train and compare decision trees with different pruning strengths. To compare decision trees with different pruning strengths, we prepare 3 tracking lists, one for training accuracy, one for test accuracy, and one for the number of leaves in each pruned tree. These values let us evaluate how pruning affects both model complexity and performance. For each selected pruning strength, a new decision tree classifier is trained on the training data. Its accuracy is then measured on both the training and test data to compare learning performance with generalization. The number of leaves is also recorded to track how pruning affects the tree's complexity. To choose the best alpha, find the test score with the highest accuracy and use its position to select the matching alpha value. That alpha is the best pruning strength for the decision tree, and the same position gives the best test score. The output summarizes the pruning results for a decision tree. It reports the Scikit-Learn version for reproducibility, compares the number of leaves before and after pruning, and shows the pruning strength that gave the best test performance. It then reports the highest test accuracy, rounded to 3 decimal places. We create a plot to compare training and test accuracy across different numbers of leaves. Each accuracy curve is marked with points, making it easy to see how pruning affects performance on the training data, and how well the model generalizes to unseen data. The plot is formatted to show the cost complexity pruning path clearly. The x-axis is reversed, so fewer leaves, meaning stronger pruning, appear as the graph moves to the right. Labels, a title, and a legend identify the number of leaves, accuracy, and the training and test accuracy lines, making it easier to compare how pruning affects model performance. This script shows how cost complexity pruning can improve a decision tree classifier on the breast cancer dataset. It trains trees with different pruning strengths, compares their training and test accuracy, and chooses the alpha value with the best test performance. It then reports how the best pruned tree differs from the unpruned tree, including the number of leaves and test accuracy. A final plot summarizes the trade-off between tree size and accuracy, showing how pruning can reduce complexity and improve generalization. Choosing alpha. Choosing alpha in cost complexity pruning means trading a little training accuracy for a simpler, more reliable decision tree. Pause. A small alpha keeps more detail, while a larger alpha removes branches that do not add enough value. Pause. This helps prevent the tree from memorizing rare training patterns and keeps the focus on stable signals, such as important churn factors like contract length or payment issues. Choose the pruning alpha by testing pruned trees on data not used for training, such as a validation set or cross-validation. The goal is to find a tree that performs well on new data, not just the training data. Grow the tree, compare several pruning levels, and select the alpha using a performance measure that fits the task and its error costs. When several alpha values give similar validation performance, it is often better to choose the simpler tree. A simpler model is easier to explain, more stable, and less sensitive to small changes in the data, which matters when results must be trusted by non-technical audiences. Choosing alpha, therefore, means balancing accuracy with interpretability, robustness, and real-world usefulness. Python code, choosing alpha. This example selects the pruning strength for a decision tree. The alpha value penalizes branches that add little validation benefit, helping identify a simpler tree that still performs competitively. We import key Python libraries for the project: NumPy for numerical work, Matplotlib for plotting, and Scikit-Learn for machine learning tools. We then load Scikit-Learn's breast cancer dataset, which will be used to train and test a decision tree classification model. We import 3 key tools from Scikit-Learn: a train test split function to separate the data into training and validation sets, a decision tree classifier to build the model, and an accuracy score function to evaluate its predictions. Together, these let us train the decision tree, keep validation data unseen during training, and measure performance on both datasets. We load Scikit-Learn's breast cancer dataset for a classification task and separate it into input features and target labels. This lets the model use the data and the correct answers independently during training and evaluation. The code verifies that the feature data and labels have the same number of entries, so every data point has a matching label. If they do not match, it raises an error. This check helps prevent training problems caused by mismatched data. We split the dataset into training and validation sets so the model can be evaluated on data it has not seen during training. Using Scikit-Learn's train test split, 30% of the data is reserved for validation and 70% for training. The split is stratified to keep class proportions consistent, and a fixed random state makes the result reproducible. A decision tree classifier is first built with a fixed random state, so the results can be reproduced. After growing the initial tree, the training data is used to find its cost complexity pruning path. This path gives a range of alpha values that control how strongly tree complexity is penalized. And the final alpha is excluded, so the remaining values can be tested for useful pruning. To choose a manageable set of candidate alpha values, we sample 12 evenly spaced positions across the available range using NumPy's linear spacing tool. We then keep only the distinct values from those positions, creating a short list for evaluation. This gives a simple, efficient way to compare pruning strengths without testing every possible alpha. We initialize 3 empty lists to track results for different pruning strengths. One stores training accuracy, another stores validation accuracy to assess generalization, and the third records the number of leaves in each prune decision tree to show model complexity. For each alpha value, a decision tree is trained with that pruning strength, then evaluated on both the training and validation data. The training and validation accuracies are stored, along with the number of leaves in the tree. This shows how pruning affects both model performance and complexity. We choose the pruning strength by finding the highest validation accuracy and selecting the last tree that achieves it, which favors the most complex tree among the best performers. The matching alpha value is then used as the chosen pruning setting. Finally, we record the number of leaves for that tree to describe its complexity. The code reports key results from decision tree pruning. It shows the Scikit-Learn version for reproducibility, the best validation accuracy found, the alpha value that produced it, and the number of leaves in the resulting tree to indicate model complexity. Create a Matplotlib figure and axis. Then plot candidate alpha values against both training and validation scores. Using marked lines for each score makes it easy to compare how accuracy changes as pruning strength varies, especially between training performance and performance on unseen data. The plot highlights the selected alpha value with a gray dashed vertical line, making the chosen pruning strength easy to identify. It is titled to show that the goal is choosing alpha for cost complexity pruning, with the horizontal axis showing the alpha penalty and the vertical axis showing accuracy. A legend clarifies the training accuracy, validation accuracy, and selected alpha marker. The plot is displayed to compare alpha values with training and validation accuracy. A vertical line marks the selected alpha, making it easier to see how the choice balances model complexity and performance. This script shows how to choose the best pruning strength for a decision tree using cost complexity pruning. It trains trees with different alpha values on the breast cancer dataset, compares their training and validation accuracy, and selects the alpha with the highest validation accuracy. It then reports the chosen alpha, the best validation score, and the number of leaves in the final tree. A plot summarizes how pruning strength affects accuracy and model complexity. Monotonic constraints. Monotonic constraints add domain knowledge to tree-based models by requiring predictions to move in a sensible direction as certain inputs change. For example, higher debt burden, more prior claims, or greater medical severity should not reduce predicted risk when other factors stay the same. These constraints do not make the relationship linear or make one feature the only driver. They simply prevent noisy data from producing patterns that contradict established expectations. Monotonic constraints help regularized models generalize by limiting unrealistic prediction changes. They prevent models, such as decision trees, from overreacting to noise or small input shifts, while still allowing useful patterns to be learned. For example, a loan default model can be constrained so higher income does not raise predicted default risk, and a demand model can be constrained so higher prices do not increase purchase probability. Monotonic constraints should be used carefully because the wrong constraint can bias a model and hurt accuracy. They are most appropriate when the direction of a feature's effect is reliable after accounting for other variables. Since these constraints apply conditionally, they help keep predictions consistent and trustworthy when one feature changes while others stay fixed. Used as part of a broader regularization strategy, they can prevent unreasonable model behavior without removing too much flexibility. Python code, monotonic constraints. This example illustrates monotonic constraints in decision trees. These constraints help prevent unrealistic reversals in predictions, and the comparison shows how constrained trees differ from unconstrained ones. The script imports the main tools needed for the workflow: NumPy for numerical work and arrays, Matplotlib for plotting, and Scikit-Learn for machine learning. It also brings in the decision tree regressor, which is used to build regression models based on decision trees. A fixed seed of 42 is used to initialize the random number generator, making the noisy data repeatable. This ensures the example produces consistent results each time the code runs. We create 80 evenly spaced feature values from 0 to 10, then add normally distributed random noise centered at 0. The target values are generated as twice each feature value plus this noise, producing a simple linear relationship with realistic variability. The code lowers a small range of target values by 10, creating unusual data points that may cause a decision tree to reverse some predictions. It then reshapes the feature data into a two-dimensional, single-column format, so it matches the input structure required by the model. The code first checks that the feature data and target data have the same number of entries. This ensures each feature row matches one target value before training begins. If they do not match, it raises an error to prevent incorrect model fitting. We create two decision tree regressors to compare their behavior. The first is a flexible tree with a maximum depth of 4, while the second uses the same depth but adds a monotonic constraint, so predictions can only rise as feature values increase. Both models use a fixed random state for reproducibility and are then trained on the feature and target data, with the constrained tree learning under its monotonic rule. To compare the two decision trees, we generate a smooth set of feature values from 0 to 10 and use it as input for both models. Each tree predicts target values across the same range, letting us see how their predictions change over the feature space. This makes it easier to compare the unconstrained model with the monotonic model, especially in terms of prediction direction. To check for prediction reversals, compare each prediction with the next one and count how often the value decreases. This is done for both the unconstrained tree and the monotonic tree, using consecutive differences to identify downward steps. The resulting counts show how well each model maintains a consistent prediction direction. The output first reports the Scikit-Learn version to support compatibility and reproducibility. It then compares the number of downward prediction steps in an unconstrained decision tree with those in a monotonic tree. Fewer downward steps in the monotonic tree indicate that the constraints are reducing reversals as intended. The plot compares noisy training data with predictions from two decision tree models. It shows the raw data points, an unconstrained tree prediction line, and a monotonically increasing tree prediction line over the same feature range. The title and labels emphasize that monotonic constraints act as a regularization guardrail by preventing prediction reversals. A legend identifies each element, and the final display makes it easy to compare how the constrained and unconstrained models behave. This script shows how monotonic constraints can keep decision tree predictions consistent. It creates noisy linear data with outliers, then compares an unconstrained tree with one constrained to increase monotonically. The unconstrained tree can overfit and produce downward prediction steps, while the constrained tree preserves an upward trend. The script counts these downward steps and plots both prediction curves to show how the constraint prevents prediction reversals. In this lecture, you learn to explain cart construction and impurity reduction in practical terms, diagnose overfitting and instability in decision trees, and apply pruning and structural constraints to improve generalization. In the next module, Module 17, we will go over forests bagging.
Thank you for your attention. See you all in the next lecture.